Hello everyone, my name is Chintan V.S. Teja. Currently, I am pursuing BTech second year in Information Technology from Institute of Aeronautical Engineering. Today, I am here to give a presentation regarding alternative assessment tool Tech Talk of the course Design Analysis and Algorithm. So, I'll continue with my presentation. So the title of the Tech Talk is Efficient Graph Search. So firstly, we will know what is efficient graph search. Efficient graph search means finding what you want in a graph in the fastest and smartest way without wasting time checking unnecessary paths. In very simple words, imagine a graph like a map of roads and you want to go from your house to a shop. Efficient graph search is choosing the best route quickly instead of trying every single route. Why we need it? Because graphs can be very big. Like, for example, Google Maps. Checking all paths is slow. Efficient search saves time, memory, and effort. So, in today's interconnected world, data rarely exists in isolation. Instead, it forms intricate webs of relationships, dependencies, and interactions. Graph search algorithms are the fundamental tools that allow us to navigate these complex structures, transforming raw data into actionable insights. This presentation delves into the core principles, advanced techniques, and real world applications of efficient graph search, demonstrating how its pivotal role in unlocking the true power of connected data across various domains. Graph search algorithms are adept at identifying non-obvious connections, shortest paths, central nodes, and distinct clusters within vast datasets. These patterns are often invisible to traditional database queries but are critical for deeper analysis and predictive modeling, enabling real-time insights. In dynamic environments, the ability to perform rapid graph search is paramount. From detecting fraudulent transactions as they occur, personalizing recommendations in milliseconds, to powering intelligent AI agents systems, efficient graph search provides the foundation for real-time decision making and adaptive behavior. Classic graph search algorithms, BFS and DFS algorithms. BFS explores a graph layer by layer, starting from a source node and visiting all its immediate neighbors before moving to their next neighbors, and so on. This systematic expansion guarantees that the first time a node is reached, it is via the shortest path in terms of the number of edges. Consequently, BFS is invaluable for finding shortest paths in unweighted graphs. It is often implemented using a queue data structure to manage the order of node visits. Explores neighbors concentrically, guarantees shortest path in unweighted graphs, uses a queue for node management. Both BFS and DFS are foundational algorithms forming the backbone of many more complex graph applications. DFS. In contrast to BFS, DFS explores as deeply as possible along each branch before backtracking. It goes down one path until it hits a dead end or a visited node, then backtracks to last unvisited node and explores another path. DFS is particularly useful for tasks like checking graph connectivity, finding cycles, topological sorting, and solving puzzles with only one solution. It is typically implemented using a stack or recursion. Explores paths to their fullest extent, ideal for connectivity and cycle detection. Uses a stack or recursion for node management. Both BFS and DFS are foundational algorithms forming the backbone of many more complex graph applications. Breadth first search. In breadth first search, we start at a vertex V and mark it as having been visited. The vertex V is at a type this is said to be unexplored. A vertex is said to have been explored by an algorithm when the algorithm has visited all vertices adjacent from it. All unvisited vertices adjacent from V are visited texts. These are new unexplored vertices. Vertex V has now been explored. The newly visited vertices haven't been explored and are put onto the end of a list. of unexplored vertices. The first vertex on this list is the next to be explored. Exploration continues until no unexplored vertex is left. In simple words, we can say that breadth-first search finds shortest path step by step. First, here are given two examples. First one is undirected graph G, and second one is breadth-first spanning tree. Explored under time is at least big O of n plus e and big O of n squared respectively. Hence, T of n comma e equal to big O of n plus e when adjacency lists are used, and time complexity of n comma e is equal to big O of n squared when adjacency matrices are used. Here is the breadth-first algorithm. A breadth-first search of G is carried out beginning at vertex V for any node I listed of I equal to 1 if I has already been listed. The graph G and array listed are global. Listed is an initialized to 0. Depth first search algorithm. A depth first search algorithm of a graph differs from a breadth first search in that the exploration of a vertex V is suspended as soon as a new vertex is reached. At this time, the exploration of the new vertex U begins. When this new vertex has been explored, the exploration of V continues. The search terminates when all reached vertices have been fully explored. With depth first search, the start state is chosen to begin, followed by some successor of the start state, then some successor of that state, and so on until a goal of state is reached. If depth of search reaches a state S without successors, or if all the successors of a state S have been chosen or visited, and a goal state has not been found, then it backs up, which means it goes to the immediately previous state or predecessor formally, the state whose successor was S originally. Here is the third search algorithm where given an undirected graph G where vertices and with vertices and edges with n vertices and an array visited initially set to 0, this algorithm visits all vertices reachable from V. G and visited are global. So, in simple words, depth first search is goes deep firstly and good for exploring. Here is undirected graph G and depth first spanning tree. One can easily prove that DFS visits all vertices reachable from vertex V. If T of n, e and S of n, e represent the maximum time and maximum additional space taken by DFS for an n vertex edge E graph, then S of n comma e equal to big O of n and T of n comma e equal to big O of n plus c if adjacency lists are used, and T of n comma e equal to big O of n square if adjacency matrices are used. Beyond basics, weighted and directed graphs. While BFS and DFS are foundational, real-world graphs often possess additional complexities that require more sophisticated algorithms. Directed graphs. Simply directed graphs are nothing but a directional graph with a direction from one vertex to another vertex. In many scenarios, relationships are not bidirectional. For instance, a hyperlink on a web page points from one page to another, but not necessarily vice versa. Similarly, task dependencies in a project flow in one direction. Directed graphs where edges have to a specific orientation are used to model these one-way relationships. Algorithms must account for edge direction as traversing from A to B is not the same as B to A. Weighted graphs. Weighted graphs in simple words just means that there is a distance calculated between one vertex to another vertex. Often the connections between nodes have an associated cost, distance, time, or capacity. This is what I meant by weighted means the cost and distance between the two nodes or the vertexes. These are known as edge weights. For example, in a road network, The weight could be the travel time or distance between two cities. In a communication network, it might be the latency or cost of data transmission. Weighted graphs necessitate algorithms that consider these values to find optimal paths, not just paths with the fewest hops. Dijkstra's algorithm. For weighted graphs, Dijkstra's algorithm is a cornerstone for finding the shortest path from a single source node to all other nodes. It systematically explores the graph, always choosing the unvisited node with the smallest known distance from the source. This greedy approach guarantees finding the shortest paths in graphs with non-negative edge weights, making it essential for navigation systems, network routing, and other optimization problems. In simple words, we can say that Dijkstra's algorithm finds shortest path with weights, which are distance and cost. A star search, heuristic driven efficiency. A star search is a smart search using a goal direction, which is used in maps and games. While Dijkstra's algorithm efficiently finds shortest paths in weighted graphs, it can sometimes explore a significant portion of the graph unnecessarily. A star pronounced A star search improves upon by this incorporating a heuristic function to guide its exploration, dramatically reducing the space. Combining actual cost and heuristic estimate. A star search operates by maintaining an estimate of the total cost from the start node to goal. Passing through the current node, this estimate is the sum of two components, g of n, the actual cost of the path from the start node to the current node, h of n, a heuristic estimate of the cost from the current node to the goal node, dramatically reduce search space. By leveraging the heuristic, A star can often find the shortest path much faster than Dijkstra's, especially in large graphs where the heuristic is accurate. It prunes away paths that are unlikely to lead the goal efficiently, focusing its computational efforts on more promising routes. This makes it particularly effective in scenarios where the goal location is known or can be reliably estimated, avoids exploring suboptimally branches, more efficient for large goal directed searches, prioritizes prompting paths. Widespread application. A star search is a cornerstone algorithm in several high impact fields, navigation systems, calculating optimal routes in GPS applications, robotics pathfinding for autonomous robots in complex environments, game AI enabling characters to find paths around obstacles in video games, resource allocation. Its balance of optimality and efficiency makes A star a highly versatile and powerful tool in modern computing. Optimizing BFS, early termination, and frontier management. While classic BFS is effective for finding shortest paths in unweighted graphs, its default behavior of exploring an entire reachable graph can be inefficient when only a specific target needs to be found. Optimizations focus on refining this process. Classic BFS, a broad sweep. Traditionally, BFS explores every node reachable from the starting point layer by layer until the entire connected component is not discovered. Early termination. One of the most straightforward optimizations is early termination. Frontier management. The frontier in BFS refers to set of nodes that have been discovered but not yet visited. Optimized queue implementations. Using data structures that allow very fast NQ and DQ operations. Parallel BFS distributing the processing of the frontier across multiple threads or processes for massive graphs. Bidirectional BFS simultaneously running two BFS searches, one from the source and one from the target, meeting in the middle. Parallel and dynamic graph search. As graphs grow in size and complexity and as data evolves in real time, traditional sequential graph search approaches become insufficient. Parallel and dynamic graph search algorithms are designed to tackle these challenges. Massive graphs. Modern graphs, such as the entire internet or global social networks, can contain billions of nodes and trillions of edges. Searching these graphs subsequently is often infeasible due to time and memory constraints. Parallel algorithms. Parallel graph search algorithms distribute the computational workload across multiple processors, cores, or machines. This involves techniques like partitioning the graph, managing the distributed queues for front-end nodes, and synchronizing the results. Evolving data. Many real-world graphs are not static, they constantly change. New users join social networks, new transactions occur, and sensor data streams in. Dynamic graph search. Dynamic graph search algorithms are designed to efficiently update search results when the underlying graph changes. Real world impact. The theoretical power of efficient search graph algorithms translates directly into practical, high impact applications across dynamic, diverse industries. Fraud detection. Graph search is a game changer in combating financial crime by representing transactional accounts and individuals as nodes and edges. Multi hop suspicious transaction patterns can be traced in seconds. This allows financial institutions to identify fraud rings, money laundering schemes, and synthetic identities much faster than traditional rule based systems, often preventing losses before they occur. Recommendation engines. From e commerce to streaming services, personalized recommendations are driven by graph search, users, products, and their interactions from a vast graph. Algorithms traverse this wide graph to find users with similar tastes or products. Supply chain mapping. Modern supply chains are incredibly complex with intricate dependencies between suppliers, manufacturers, distributors, and retailers. Graph search can dynamically map these dependencies identically, critical nodes, and assess risk propagation. Conclusion. Efficient graph search plays a vital role in computer science and real-world problem solving as it enables quick navigation through complex networks by finding paths, connections, or optimal solutions with minimal cost. Algorithms such as BFS, TFS, DISTRAS, and A-star highlight the different strategies to balance speed, memory usage, and accuracy depending on the context, whether the goal is shortest path discovery, connectivity analysis, or heuristic-driven exploration. Their applications extend across diverse domains, including artificial intelligence, social networks, dynamic data mining, routing, and bioinformatics, proving their immense practical value. In essence, efficient graph search is not just about traversing nodes and edges, it is about transforming complexity into clarity and unlocking possibilities for scalable, intelligent solutions. Thank you for the opportunity.